There we go. Okay, good evening, everybody. Welcome to our regular SOAREX meeting. And before we get started, I've, I'm going to read the disclaimer. Please note that all our meetings are recorded and made available to the public for viewing on our YouTube channel. By participating in the meeting, it is understood that you have accepted these terms. So, tonight on the agenda hot list, uh, we've got Dave going up first with the Beacon project, and then we'll have Peter with LT Spice exploring the measure and AQL functions, and then myself with an update to the DCR. And then, if we have any time left, we can discuss or ask questions. So, you ready to go, Dave?
Hey,
Okay, take it over.
I got one question from Michael though. Hey, Michael, what are all those certificates on the wall? You're on mute. Okay. Yeah.
What's the question?
What are all those certificates on the wall behind you?
Oh, they're DXCC certificates
Oh, okay.
for
Okay.
mixed
Here,
and
here I
mixed
am
and
thinking.
CW and
Here I am
10
thinking
through
some
20 or something. Yeah.
engineering. Here I am thinking it's some kind
Yeah.
of engineering fineness award or something. You know.
No. Nope, haven't got any. Nope, that's all. Yeah.
Okay. Let me start sharing my screen. So can you guys see my screen? Okay.
Yep. Yep. No problem.
Okay. So what I want to talk about today is my Beacon project, but I kind of lied. I'm actually going to talk about a lock-in amplifier, and it's a lock-in. It's a Beacon that's doing a mode that I made up called QRRS, and I'll explain that in a second. But I want to talk about the Beacon I'm using and this thing called a lock-in amplifier. So background, what I'm going to do is just going to talk about why am I doing this, some fundamentals about a lock-in amplifier, a little bit of design, and then I'm going to show you the results that I'm getting, which I want to get to the results because that's more interesting. So just my usual caveat, I have no idea what I'm talking about. Don't listen to me. This is just rantings of what I kind of figured out. Could be right, could be wrong. Take what I say with a grain of salt. So as usual, here's some references if you want to dig into a lock-in amplifier. There's a couple of really good videos that I use to learn about this mode. And as well, I ran across this guy, Mark Shitnicker. Sorry, Mark, if I butchered your name. But he's got a really good video about how to measure signals with noise. If you've got a really noisy signal, there he's showing an example of a really noisy signal, and he's able to pull out the signal from the noise with just a simple scope. Very interesting video. So the reason I'm doing this is that the 2024 eclipse is coming up, and HamSci is put out a request for people to get on to Whisper and RBN and use their Grape module so that they could glean some physics about the ionosphere. And I see this as an excellent opportunity to do some experimentation of myself. So, the 2024 eclipse is coming up. It's in 2 weeks. What do we do? So, the eclipse lasts for maybe 2 or 3 minutes at most. The entire duration is maybe 2.5 hours, 2 hours, just over two hours. And so where I am, it's probably going to be seconds, probably going to be 10, 20 seconds, because I'm not at the point of totality. So nighttime is going to be less than a minute, and sunrise, sunset's going to be, of the order of 2.5 hours if you're in the maximum air, in the best air area, but it'll be much shorter for where I am, maybe, less than an hour. So we talked before, and, some of us said, we'd run Whisper. That'd be great because Hamsci could take that data. And if you've got an aggregate of hundreds of people running Whisper, it averages out that you can get some pretty good measurements. But for one person using Whisper, it's not a very good platform because, number one, it transmits in even minutes and it takes 2 minutes to complete. So if I've got like 10 or 20 seconds of night, Whisper is it's a non-start for me. It's great for Hamsci, but for my purposes of my experimentation, not going to work. There's RBN. And this is typically a spotting network. It's not meant for propagation, but it can be used. It's used for making contacts. And the problem is it does not identify every transmission. So if you transmit a CW signal now, 10 seconds later you transmit the same CW signal, it's only going to show one spot, that first signal. So you don't get a granularity over, tens of seconds. It's probably over minutes. It's only going to spot you over several minutes. So again, not a good non-start for me. So I decided to build my own beacon and develop my own propagation mode. So first of all, I looked at something called QRSS, which is like the QRS, which is the slow code. Everyone's familiar with QRS, and the extra S means slow. So it's really slow, but it's meant more for visual decoding, and it's slow. I guess you could automate it, but it's going to take quite a bit of processing to go and do that. So I needed to develop a mechanism to detect a transmission. So I decided to send a short CW identifier saying, V3OI, and then transmit a constant carrier for about 15 seconds or so. And a carrier is much easier to detect. And I need to also make the carrier short enough so I'm not going to piss anyone off. Because if you got a very long carrier, that's that's noise. You could be generating harmful interference, I think it's called. So you want it short of the order of an antenna tuner, going off. So this is just an explanation of what QRSS is. And it's just, you got, if no one doesn't familiar with this, it's where you've got your dots and dashes or several seconds. And I've seen some people where they take, 30 seconds to transmit a dot or a dash. And what happens when you do that, you could go on a visualizer and you could actually see the dits and dots. Now, QRSS does not exist. It's something I fabricated. So the architecture I'm using for my beacon is I've got my beacon. It's going to transmit this QRRS signal. I'm going to use a web SDR to listen for it. Then I wrote a little program in Python that's using this thing called a lock-in amplifier, which I'll talk about in a second. And I'm using that to detect the signal. And right here, you can see it's detected 3 signals here. And also what I'm also doing is I've built this completely different project. Is I built a solar tracker, and during the eclipse, it's going to be following the sun. And it's got some sensor arrays. I've only got 3 sensors here, a solar cell, UV, and an IR camera mounted. And it's also got IR sensors inside this little crosshair thing here. It's going to have cameras and temperature sensors and other sensors mounted. And it's going to track the sun and make measurements during the eclipse. So this is my plea, my request for help. This is one of the reasons I'm doing this talk, is I'm putting out a plea. I need help. And if you could use a web SDR and tune it in and run my Python program to listen for my signal, or you can use your own radio, provided your radio is connected to a sound card on your PC. Then you could use my little Python program to detect my QRS signal. You could save it, and then I could use that data to see what happened during the eclipse. So if any of you would like to help, let me know. I'd certainly looking for help. So how do you detect that carrier now? So I talked about my QRRS is going to send out a short identifier and a carrier. So how do I detect that carrier? Well, there's lots of ways of doing it. And I just listed a couple ways here. One is using a fast Fourier transform. Not going to go into that detail there, but there are forms of a Fourier transform. There's a fast Fourier transform, discrete Gertzel algorithm. If you go back to my talk on fast Fourier transform, I talk about that. There's a link there. You could go back and listen to that. You could also use correlation. And a fast Fourier transform is another form of a correlation. You are doing a correlation. But when I talk about this, I'm talking about doing a convolution. In my video here, I talk about how I use signal correlation, something called autocorrelation, to detect RIDI and PSK. And that's one way of doing it. And the reason I did that was because I used a 16 megahertz Arduino. The the Mega board. I use that to detect RIDI and PSK. And as I was going through trying to find alternate ways of doing this, because ideally I want to do it, I'd like to do it in a microcontroller. I ended up not doing it in a microcontroller, but that's not because it cannot be done. I stumbled across this thing called a lock-in amplifier. And this is showing a typical lock-in amplifier. It's a lot of money. It's used to detect pull signals from noise. If you've got a very noisy signal and you want to get that signal, this thing can pull that signal out of the noise. So what I want to do is I want to talk a little bit about the lock-in amplifier. Now there's a really good video here. I cited this on my reference, and it talks about how a lock-in amplifier works. It also gives an example of how a garage door sensor, you know the sensor at the bottom of your garage door opener, when you break it, the garage door stops. Well, if that sensor is in light, it's still able to detect when you break that beam. So, and once it's in direct sunlight, it's noise. So he talks about how the lock-in amplifier is used to do that. And again, you know, most of the lock-in amplifiers I saw were hardware-based. Very little I saw about software until I ran across this presentation here. It's not about software, but it's just how it works. But he breaks it down so simply that you're able to go and develop some software to do this. So basically, how does it work? Very simple. You've got your signal. This is your signal you want to detect. By the way, am I still on the air here? Can you guys still hear me?
Yep, we can hear you.
Yep, you're
Okay.
good.
Okay, so the red signal is a signal you want to detect. In this case, I'm keeping it simple. It's a pure sine wave. Okay, so you've got this pure sine wave. Say it's 1300 hertz. Okay, then you've got a reference signal. Your reference signal must be the exact frequency of your input signal. It's just a reference signal. So what you do, you multiply the two signals together. You take each point and you multiply it together. Well, when you multiply two signals together in the time domain, you're doing mixing. That's basically you're mixing the two signals. So if you have a 1300 hertz signal here, reference signal, 1300 hertz reference signal, and a 1300 hertz actual signal, you mix them together, what do you get? You get the sum and differences. You get 1300 plus 1300, you get 2600, you get 2 times the frequency, but you get the difference, which is 0. which is a DC, 0. So you get 0 hertz. So, and that's where the trick here is. So this is showing the multiplication. This is the red is my signal trace, and the green is the resulting multiplication. Now I shrunk it. It's not drawn to scale. It should be 2 times the frequency of the red signal, but I just drew it this way for dramatic effect. Okay, so here you can see the red signal. If you take the average of the red signal, it's got a negative, goes from -1 to +1. And if you average this red signal over time, you'll get 0 because it's a bipolar signal. It's crossing equally across the 0 axis here. However, if you look at the resulting multiplication signal, it's going from 0 to 1. It's going up. It doesn't cross 0. It's a unipolar signal. Now, if you average this out, because it's going from 0 to 1, you average it out, it's going to come out to 0.5. So it's got a DC offset. So now it just so happens when you do this, magically, the DC offset is always half the signal amplitude. That's a really cool feature because all of a sudden you could use a lock-in amplifier to measure the amplitude of the original signal, which is kind of cool. So I'm going to talk a little bit. I have to give a little bit of background now about how my software works. It's all visual, but hopefully I don't confuse anyone here. So I'm going to be using this frequency spectrum here along the x-axis here. This is showing frequency. This is a fast Fourier transform, so it's kind of like an SA, spectrum analyzer output. You're seeing frequency along the bottom, and along the y-axis, it's just telling you the magnitude, how strong the signal is. So in this case, we've got a 1300 hertz signal, and it's just AC. And then down here at 0 hertz, that'll be DC. Okay, so it's showing that you've got no DC associated with this signal. So this is just another way of showing that same diagram I did, but now you can see here, it's centered around 0. So if you average this, it's 0. There's no DC offset here. So if you take the fast Fourier transform of that, you'll get the this is 1300 hertz. You'll get the 1300 hertz peak in the FFT, and you'll get 0 at 0 hertz because there's no DC. Right, so now let's add some DC to that signal. So in this diagram, 0 axis is down here. We've lifted this signal up. We've added some DC. So if you look at the average, you take the average of this signal, it's right here. So you can see it's a unipolar signal with a DC offset here. So if you were to take the fast Fourier transform, you'll still get the 1300. This is not drawn to scale, by the way. So you'll still get the 1300 hertz signal here. But you now get a spike here at 0, which is the DC. That represents the DC signal here. So now, what happens when we say we have a signal outside? We've got this spectrum here. We've got an unwanted signal, but we just want this 1300 hertz signal. Well, we could do a low-pass filter. And when you do a low-pass filter, you just get rid of this signals beyond this point here. They get attenuated based on this roll off here, and you'll get your signal, but you'll also get the DC signal if it's present. I think some of you are seeing where I'm going with this. So now, let's just say you've got a DC signal, and you've got an unwanted signal out here. You've got some kind of DC offset, but you just want to get your signal alone without the DC offset. Well, you use the bandpass filter, and that bandpass filter will only pass the frequencies within the pass band here. Everything beyond whatever the 3 dB points here are, it's going to get knocked down. So now, what happens if we want to detect the DC offset? We got a DC offset here, and you could, some of you should be able to see where I'm going now with this. So now, if I've got my 1300 hertz signal and a DC offset, but I only want to get the DC offset. What I could do is low pass filter it, but my cutoff now is going to be maybe 100 hertz or 200 hertz, where I'm just going to knock out this main frequency here, and I only get the DC signal passing through. So let me tie all this together now. So a lock-in amplifier and DC. I've been talking about DC a lot. Let me tie everything together now. So noise is typically bipolar and typically has a DC average of 0. Noise typically has no DC offset. This is key to a lock-in amplifier. So if you've got a signal with noise and you've got your reference signal with noise, so your signal has noise, your reference signal has no noise, and you multiply them together. Remember I showed you get your signal at twice the frequency plus a DC offset, provided the reference signal is the same frequency as the signal. Now, noise will not contribute to the DC offset because it averages out to 0. So that's the trick of a lock-in amplifier right there, is it removes the noise because it assumes the noise is going to average out to 0. If your noise doesn't average out to 0, then this is not going to work. So the trick to make this work, this only works for repetitive, unmodulated signals. So a carrier. That's why I said, okay, I'm going to send a carrier. So the reference signal must be the same frequency. And after multiplying the signal and reference, if there's any DC present, the signal's there. The reference signal is in that signal you're trying to detect. Now, something else happens if your reference and your actual signal are out of phase. Let's just say they're 180 degrees out of phase. You multiply them, you get 0. So which means that this algorithm doesn't work. It'll come out as 0. There's no DC, so it isn't there. So what you have to do in that case, you have to use quadrature signals. You have to, your reference signal, you have to take the cosine and the sine. Now, the thing about these quadrature signals, they're orthogonal to one another. They're at 90 degrees. So if you take the result you get by multiplying sine of your signal of your reference and cosine of your reference, you take both of those, they're at right angles to one another. And if you want the magnitude, you're basically, it's a right angle triangle, and it's just the sum of the squares. High school math or high school vectors or algebra or whatever. So how does this work? So let me tie it all together now in a nice pretty bow. So you've got your signal here with noise. Okay, so the first thing you do, you pass it through a band pass filter, and what that's going to do, that's going to remove any higher frequency components, and it's going to remove any DC components. Now, one of the things I didn't mention is that, let me go back to this signal here. One of the things I didn't mention here is that if this reference signal is a harmonic of your main frequency, it'll show up as a DC offset. So you want to filter this to remove any harmonics of your main signal. So you're getting the signal alone. Because if you run this with any harmonics of the signal, it's not going to work. So where was I? I was here. So you do your bandpass filter to only get your signal that you want to see if it's there. You're getting rid of anything below it or above it. Then you're going to multiply that by your reference signal. Now, in actual fact, you have to multiply it by sine and cosine. You got to use the quadrature, but let's ignore that for the time being. So you're just going to multiply it by your reference. Then the output, you're going to low pass filter because we want to get the DC. We want to see if the DC is there. And once you low pass filter it, you'll get a diagram like this. You'll get a graph like this. Now you do get some oscillation here because that low pass filter is not ideal. It's not saying 0 hertz or nothing. It's actually got some bandwidth to it. So it may have a cutoff frequency of say 100 hertz or 200 hertz. So what you're seeing here is what's falling into that pass band. You're seeing 100 or 200 hertz signals coming across there. But if you look at the average, definitely you're getting a DC offset here. So this signal is present in that in this signal here. So what I do is I also take an FFT, and after the bandpass filter, I also take an FFT, and I think hopefully you could see that. So if you take an FFT of your bandpass filtered data, you get this. Now it kind of looks strange. You got a whole bunch of points here, but you get nothing out here. And that's because the bandpass filter has knocked everything down here. This is your pass band here. And you can see the 1300 hertz signal is actually present. So the FFT is actually doing a great job. It actually detected that signal in the noise. And all this junk here is just noise at that frequency. Any noise that's around that frequency, around the 1300 hertz, it's showing up because you can't filter that out. So what I did for testing is I wrote a little Python program, and my Python program, I defined the sample frequency, the maximum signal amplitude, the maximum noise amplitude, and I also played around with adding a DC offset just to make sure that the bandpass filter was working. So I generated some data, and I generated 1300 hertz, which is what I wanted to detect, 2300 hertz, and then 1000 hertz, something close to 1300 hertz, and then I put in a whole bunch of noise. And in this sample I did here, I did all kinds of different samples, but in this one I'm showing, my noise is twice the amplitude, twice my signal amplitude. And so the red is my signal, and the blue is my reference signal. So you could almost say that signal, the blue signal, is there in the red signal. It kind of looks like it. But if you go through, you do the bandpass filter, you do the FFT, then you do the lock-in, definitely you see the signals present. The FFT shows the signals present. That's 1300 hertz right there. And this is showing the DC. Here, offset. Now, again, the interesting thing is, remember I said it's supposed to show half the amplitude? So if the amplitude's 16, this is showing just a smidgen above 8. So it's showing roughly about half of the amplitude here, right? And it's kind of interesting. The FFT is also doing the same thing. It's showing the amplitude, half the amplitude of that signal. And I think it's because the way an FFT works, you're getting a mirror image. I don't want to get into it, but if you do an FFT, you have to take half of the spectrum, so you get half of the power, something like that. So in my last presentation, I talked about how I used a buffer driver here to increase the output of a BS170. You could go back if you missed that. You want to see how that works, you could go and look at that video. But basically, I prototyped my beacon, and I'm driving it with this buffer driver chip here. And my last presentation, I showed that I was able to get almost twice the power output without the buffer chip, and I was able to get at least 1 watt right across the HF spectrum. So from that, I went and I created my beacon. And you could see Arduino Nano there. There's the SI5351. And I decided to use a real-time clock instead of using a GPS. And it works out just fine. I was able to do whisper with this real-time clock. It works. I'm able to do whisper. So with this, I wrote a Python program to configure it, as opposed to going in and configuring it via your program or using a CLI, because anyone who knows the way I work, I just love a CLI, a command line interface. So I configure everything using a CLI. So in this case, I decided to write a GUI, and you check what you want, and it configures the board for you. And so this is written in Python, so it you could define what modes. It's got 3 modes. You could use CW for RBN. You could use Whisper, or you could use my mode QRRS. And you could define when it's going to start, how long it's going to last, how long it's going to repeat, and so forth. And you could also calibrate the clock. You could tell it to write what your actual PC clock, so you could calibrate the clock for your real-time clock. And so for the data capture, I used Python. And so you need a sound card. You got to have a sound card connected to your radio. It needs audio coming from the radio, and the radio is tuned to the QRRS frequency, and it listens to a sound card device, and it gets the data from the sound card, and then it performs, the steps I just said. It does a bandpass filter. It does an FFT. It generates the signal, and you define the signal you want to define here. So if it's 1300 hertz, you say 1300 hertz. It generates the reference signal, multiplies them, does the lock-in, does all that, and it can also save it to a file. So now let's talk about the data. That's it. I'm done. I just want to show you some of the data I captured. So this is one output I got, and clearly you could see there's 3 peaks here. So now the QRRS wakes up. I think it was every 15 for this test, was every 15 or 20 seconds. So you could see it's very repetitious in nature. You could see peaks here. The green, the bluish green, I'm colorblind, peak here, that's what the lock-in is predicting it's seeing, and the green is showing what the FFT. And then this is telling me what the lock-in frequency thinks it is, and this is telling me what the FFT frequency it is. And then I got a little flashing icon here that says, bloop, 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 I found 1324, frequency of 1324 hertz. So here's another look at the same thing again. Now, I'm using Python. I'm using the Python lib, I can't remember what it's called, library. And when you plot in real time, it kind of compresses the data. So you get all the peaks kind of squished together. So this was over some time. You could definitely see some weak signals here. Then you see some stronger signals here. And you're seeing, again, FFT and the lock-in calculations there. And this is just showing my Digital Master 780. It's showing my QRSS. You could see the CW here, and then you could see the carrier being broadcast here. And here's the next set of slides is just some different views. So here you can see you can see that there's a peak here, but the lock-in predicts a peak, but the FFT doesn't. Here, both FFT and lock-in predicts the peak, same thing here. So, and the key thing is, if you look, they're evenly spaced. So it's definitely detecting a signal there. Here, you could see the same thing here. You could definitely see the signal present. This is just another view here, the lock-in popping up saying, hey, found a frequency. I'm seeing it at 1290. The FFT saying it at 13 hertz. And this next test I'm going to show, it turns out as I was doing this on the radio, there was something right adjacent, like 100 hertz away, and it's Olivia or something, and it was quite significant. It was quite loud. So, and I was still able to detect my signal even with that signal present. It still worked. And here now, if you listen very carefully, you can hear the signal. At first, you're going to hear it where it's really, really, really weak. You could barely hear it in the noise. I don't know if you just heard the carrier there. And here it is with very loud. So and then this is just an export coming out into Excel. You can it exports the data into Excel, and this way you can expand it, and you could better look for peaks. And this is just showing two different views. One is showing the FFT grayed out, and you're seeing the lock-in, and this other one is showing the lock-in grayed out and the FFT, and you could kind of see the peaks between them. And here you could definitely see something way down here in the noise. I've expanded it, so you're seeing a signal there, and that's it. Now, just in final, one of the things, the reason why I chose 14.100 is because 14.100 is for unattended beacons. That's where you would put a unattended beacon. So it's perfectly okay putting this on 14.100. So that's it, and I'll take questions now.
Okay, saw somebody's hand go up.
Drew.
Okay, go ahead, Drew.
Yeah, Dave, I'm quite happy to record. 14.1 is no problem, and I have an SDR to do it. Now, I was wondering, rather than set up a receiver, is it of value to simply record on that frequency and then run your Python script following that?
Absolutely, because it's trivial for me to go in my Python script and tell it to pull in a file as opposed to listening to a audio device. All I got to do is take out that module.
Any of the SDR plays and that sort of thing, they're quite happy to record for a finite time on a certain frequency.
Sure, if you could do that, but do it for like maybe a couple minutes before, like if you're.
Oh yeah, no, you can record for an hour. It doesn't matter. It's just.
Oh yeah, okay. If you could record for like
space.
all I'm looking for is about 7 minutes, 7 or 8 minutes.
Sure.
So about 3 or 4 minutes before the main time, and then 3 or 4 minutes afterwards. So if you could record for like 10 minutes, that's perfect.
Now, of course, because you and I are going to be subjected to the same eclipse at the same time, I will lose you at the time you want to be recorded.
And that's perfectly fine. This is just experimenting. I'm just trying to see what's going to happen right now on 14 megahertz. You may not hear me because you may be too close.
Oh no, not for 20, not for 20 meters.
Okay. Well,
what are you using to broadcast with? What's your antenna?
I have to make an antenna.
Indeed. I'm going to make a suggestion. I'm going to suggest that we NVIS it.
Yeah, but I wanted to get to other places. Sorry, Peter?
I was going to say 20 meters and Nevis doesn't get along.
Well, agreed, but I think if you follow the concept, I agree. It's better on 40, no question. But I was just thinking that if you do it on, it will theoretically also apply on 20. It just, I'm just thinking instead of going for a hop, try it that way.
Chances
and we have a chance to test this out ahead of time. We can try it ahead of time.
yeah, I'm hoping that I'm going to have time, but uh, I am not a very good antenna maker. So whatever antenna I'm going to make, it's probably going to be NVIS.
Well, speaker wire and some coax is your friend. A balun is a nice thing to have.
Yeah, what I'm going to do is I've got a bunch of NFED
Okay.
transformers. So I'm probably just going to get and I've got a 20 meter because that was the very first antenna I made. First time I got on the air was using a 20 meter, and I still have that transformer. And all I need to do is just cut a piece of wire, throw it up in a tree, and I know that works because that's how I made my first contact.
And what is your output power?
It's 1 watt.
1 watt.
Yeah.
Do you have any friends who have pigeons?
What do you mean?
It's got a better shot at making it here.
Yeah.
But we will attempt it. We will do our experiment. I'm quite happy to throw a machine on to record it, and whatever antenna configuration you would like me to use, I'm happy to do so.
Keep in mind that this mechanism I developed is for pulling a signal out of the noise. So you may not hear it, but if the signal is there, the lock-in algorithm will pick it up.
I'm used to that. I have a colossal amount of noise. I'm going to put this on a battery run operation outside so that it doesn't get the inside house noise.
I think Michael was next.
Yeah, Dave, would you mind re-showing this? I think it was the second slide that had the references on it. I'm going to photograph it so that I can look at it later. Was it that one? Yeah, I think it was. Hang on.
Am I showing am I still showing my screen?
Yeah, I can see it. Yep.
Oh, okay. I thought I turned off screen share. What I could do is I could post it in the chat.
Okay, that'll be good too. Thanks.
Anybody else? Go ahead. I can't see who's. Oh, okay. Anybody else have questions for Dave?
Yeah, Charlie does.
Sorry. Go ahead.
Hey, Dave. Actually, I'm kind of suspicious you may have the opposite problem in that you're actually close enough that I suspect that this will get picked up by ground wave, in which case the eclipse may have like no impact at all.
Yeah, I don't know anything about ground wave. I always thought a ground wave was typically more so, line of sight, maybe beyond a little bit of the curvature of the Earth, but it certainly doesn't go. I don't know.
Yeah, which it should follow along. It should follow along the Earth. It's mostly line of sight, but it will kind of follow the curvature a bit. And like you're really not that far away, right? You're probably 300 kilometers or something between the Kingston and where you are. So
yeah, because I did do an experiment with Peter, where I had Peter and Peter, I think I used my beacon and I sent you CW using my beacon, and you were able to hear it using 40 meters.
For sure, 40. Yep. There was there was something you sent that I didn't hear, but I can't remember what it was.
Well, 40 is certainly a better frequency for this kind of thing.
Yeah, you're definitely going to have to try and get NVIS going, because otherwise it's not going to use the ionosphere, in which case, there's no value to the test. You won't see anything in the test.
And that's why I said I'm going to be using a web SDR. I'm going to try it, and I'm going to pick a
far
site
away
that's,
place. Okay.
yeah, and where I'm going to be able to pick it up, and just for antenna alignment, all that kind of stuff, time of day, make sure that in the middle of the day, like I think the eclipse is about 3 o'clock, so around 2 o'clock or so, as long as they could hear me, then that's working, and I can tune. I'm going to take a laptop with me to the site, have my cell phone, have that on a hotspot, connect to the web SDR, pick the audio up, and run it through my Python program.
Yeah,
That's
that
what I
makes a lot of
do.
sense. If you can get to one of the web SDRs, there's some out on the East Coast that would be probably a good choice. And I'm not sure where they all are anymore, but thought there was one out around Halifax. That might be a good one.
Okay, Peter, go ahead.
Yeah, I'm thinking, even if running the test and it is a ground wave, your results are going to show, because if you see the signal and there's no real increase in the amplitude or anything like that going as the eclipse is progressing, there's no variance there, then you're going to know that it was ground wave that you picked it up, right?
Yeah, correct. That'll be true, Peter. And there's always something to be, and that's what, like, I love data. I love numbers. Like, and that's what I want to get, the numbers. I want to be able to go and look at the numbers and see what I'm getting. This is more for me, just dicking around, just playing around. I love building things, trying things. It may not work. I may not see anything. I may not get anything, but it's going to be a hell of a ride getting there. It's a good learning opportunity, right?
Okay, anybody else?
Oh, and Dave, I'd like to give you a hand, but unfortunately, I'll be overseas and can't help you with this one. Next time.
Dave, if you'd send me an email, a call sign at Gmail, just so I can figure out what you want me to do.
Sure.
You mentioned something about a sound card that I missed.
Yeah, no, it's just if you're going to be using your own radio, your radio has to be connected to your PC. You got to have a sound card.
Well,
but you said you've got a SDR, so that's a non-issue. All you got to do is just tell the software what sound card is got the audio.
Oh yeah, no, that part of it's fine. I just wasn't sure. I just want to make sure that I've done what you want me to do. So you just list down those things you want me to accomplish, and I'll just set up a little robot and it'll do it. The Raspberry Pis are brilliant that way.
What I'll do is I'll post the Python script. I'll put it on my GitHub account, and I'll post a link. Whoever wants to take it, play around with it, you're welcome to it. If you want to modify it, change it, I don't care. Go nuts.
Sounds good.
So up next is Peter. Take it away.
Okay. And we can see that. Can we see that?
Yep.
Okay.
Yep.
All right. Incidentally, I just downloaded the new version of LT Spice, and so this is the opening screen. Their new toolbar at the top is I didn't like, so I went back to their legacy toolbar up there. So I've not really done too much with the new version. Okay, so how this all started was one of the local hams here, Doug, the call sign escapes me at the moment. He has, I guess you could call it a hobby car. I forget even what it is right now. And the electrical system on this car was creating a lot of problems for him. The insulation was cracking on it and causing issues, obviously. And he decided to rewire it, and at the same time change the lighting out to and change them over to LEDs. And there's a bunch of other things he's doing as well. So he went through the exercise, and he got you got a system working on the bench, and you can see where this is going to go. Installs it in the car, and of course it doesn't work properly. Sometimes it worked, sometimes it didn't, and if it did work, it was very sporadic, so there was something wrong. So he went back in and decided to experiment a little bit with his circuit on LT Spice. So he came into one of our breakfasts on Saturday, and he started to talk about this, and this is the circuit that he he developed. So he would and he would just go through and say, okay, I'll try the Q1 transit, the 2N222 or whatever he picked at the time, and he'd go through the run, and then he would measure it like this, and he would expand out, and then he starts looking at the waveform, and we all know how to do all this kind of stuff here. And this is the exercise, the first and second cursors. Place it somewhere, and again, place it somewhere. And then, of course, on the bottom left, he would make a notation of the rise time. And what he determined when he was running the simulation, first, he realized that the rise times and the shape of the pulse was going to be the culprit of the activating the LED. So he went through several transistors, and this is the process he would go through. Change the transistor, run the simulation, make some measurements and whatnot, and then go from there. So I thought to myself when I saw this, I thought, well, there has to be a better way to go through what he was doing, because one of the problems with this is, unless you're taking screen captures and all this stuff, is comparing the waveforms beside each other. So I took his circuit, and this is where I come up with the let's complicate things in order to make things simpler. And this is what I came up with. So basically it's the same circuit. And the first thing I did was come up with using the step command. I think few of us know what the step command does, but in this usually we're doing it where we're stepping through different values of capacitors or resistors. In this case here, I did a list, and I'm going to step through different models of transistors. And what you need to do there is, in your list, identify 1 through 5, in this case, because I'm going to use 5 transistors. And you put the statement in .model, and then the 1 through 5, and then something that says AKO, and then the transistor that you want to use. And the AKO stands for a kind of. So which always struck me as kind of a funny terminology in a program. But anyway, that's what it stands for. And so now when you run your simulation, all 5 of these transistors will come up on your screen. So that was step 1. The next thing was to measure the rise time. And using measure statements, I felt, was the way to go, because where do you place your cursors? And when we're talking nanoseconds, you don't have to be off very much to get an accurate read. So how, when you're going from one waveform to another, how do you determine, where those exact spots are at the same point on each waveform? So the first thing I did was, measure the voltage out. So there you can see the top there, right here. My variable voltage minimum, and I'm measuring the minimum voltage on the out, and the same thing with maximum. So the next thing I had to do was determine for making the measurement for the rise and the fall time. And that's when I came across, there was an industry standard for this sort of calculation, and they do it to 10 and 90% of the waveform. So the next 2 lines is getting that number for, in this case, I call it VL and VH, and that's for measuring your rise and fall times. So now I take the statement here, measure, and I'm saying TR1, and when the voltage out is equal to VL, which is your 10%, and forget about the I might as well explain. The TD equals 0. I never did figure out how it worked. I left it in there because I figured it would be a reminder to me and to go back and see if I could ever determine what it actually did, because I could change that value somewhat and it doesn't make any difference. So unless somebody here knows what it might be. And then
Isn't
the
it
rise.
time delay, Peter?
Well, that's what I thought, and I tried playing with the numbers, and it didn't do anything with the results.
Mm.
So I'm not too sure, and since I picked this out from somewhere, who knows what the original author was coming up with. And then this rise is telling me make the measurement on the second waveform. You could put in any waveform you want in there, 3, 4, 1, even if you want. And again, this is the second measurement that I call in the T2R on the high side, so the 90%. I got curious while I was doing this. I played with it on the fall as well, but for this exercise, it's not important. And then the next statement down here is where it is simply I'm just taking the T2R and the minus the T1R to come up with the rise time. So, and then down here, I was just curious about the frequency. So I just went through the math here, the formulas for calculating out the frequency. And again, statements are pretty normal here. Just of note, when the waveform gets at the 0.2 voltage level, then make the measurement on the second waveform. And then on the next time one, same thing, 0.2 volt, and on the third waveform, and then you just do the math for the frequency. So that's what I did. And you can run it, and you don't actually need it because you got all the statements. You can actually go straight to your error log, although in this version, it's not called an error log anymore. But we can click on here. And now you can see all 5 transistors and how they're behaving. And you can see here, this particular transistor is quite a quick rise time, and compared to some of these other ones that are over here. So that's a good way of doing that, just to make the direct comparison that way. But again, on your what used to be called the error log is now called the SPICE output log. You get, and incidentally, this doesn't crop up on my earlier version with all these warnings about multiple definitions. And looking into it this afternoon, what it turns out is this apparently has been going on for a long time. The model file, the BJT definitions file, analog devices has duplicates in there. And this is what this warning is. So it has nothing to do with your simulations if you see it. So you can ignore it. So here's all your calculations that are going on. And then here's the important one that you want to look at. And if you take a look at here, the quickest time here is your 4th step. And that's the 29 nanoseconds rise time. And so it's quite easily that you can determine which one's giving your best performance in this regard. Let's see, what else was there? Oh, and then the frequency calculation down here is, pretty much 1 kilohertz. I thought there might have been something else. I guess that's about it here. Now, one other thing that's going on, Phil HST here has written I haven't got it running up on this computer yet. This is a brand new computer, actually. I picked it up yesterday. My other one blew up, and I just managed to get a few things in here for tonight. But he's got a script that he wrote that will read one problem with the error log file is that once you read it, you've got to get rid of it in order to run the simulation again. Every time you make a change, and then you open and close. So if you have a second screen, this script will put your log file on there and leave it up there all the time. The other nice thing about it is when you look at this particular log file, you got all these equations in here, or measurements and all these type of things, but you're only like in this case here, we were only interested in this one little segment, and you can put in this script. All I want to see is just this set of data, so it will just pick this data and display it on this little log file and just ignore all the rest of it. So, but I like I say, don't have it ready to show off here just yet, but that seems quite a good idea. I don't think there's anything else here. If you do go through these measurements with the rise times and the timing of everything, you will see that it does come up pretty accurate. And where the 10 and 90% rule is basically in around here somewhere for the 10%, and the 90 is somewhere up in that particular neighborhood. Anyway, that's all I've got.
Go ahead.
So which one was fastest?
Oh, this transistor right here, the 2N2369. I forget which transistors Doug started off with, and then when I showed him this, he did say, "Oh yeah, that's a transistor." He ultimately ended up picking up, but I'm not sure if it was this particular one because it's been quite a while since he had done this, and then I developed all the rest of this stuff. But in this particular case, it's the 2369, the fastest, and I think it's the 2222 one that's the worst of the bunch.
Okay, I think Michael was next. Go ahead, Michael.
Yeah. So, Peter, you mentioned at the beginning that the menu bars are different. So, which one of them is LT Spice? Which ones are which ones did you use?
Well, this is the latest version of LT Spice. If you go to Analog Devices, this is the latest one, version 24, whatever. And it comes with a, how do you see? Is it in here? I can't remember where you change it. Settings.
But you
Oh yeah, here. So in here in settings under operation, you got legacy or default. So there's default. So that's how it comes. Like this.
Oh, okay.
I didn't like that, so I just went into here and just changed back. They've got a box here. You can change it back to legacy.
Oh, okay. Thanks. That's good.
Go ahead, Dave.
Yeah, Peter, that's excellent. That QN PNP is excellent find. That's really nice because there's been a ton of times where I had to manually go and put in transistors just to see how they would behave. So that's a really good find. The other thing, so a couple of questions. One, do you know, is this unique for this version of LT Spice?
Which?
That QNPN?
No, that's just what I called it. That's the variable. So what you do for your transistor over here before? Sorry,
okay,
yeah, you just
okay, but that sorry that okay. Let me rephrase the question. That was a stupid question. That whole doc model 1 AKO colon 2N, is that available in other versions of LT Spice, or is that something new in this version?
This is a directive that you write out in your up here. Your Spice directive. This is Spice directives.
But is that Spice directive recognized? Because you are running the latest and greatest version. Is that recognized? Is that Spice directive recognized in prior versions of LT Spice?
Yes.
Okay.
For sure, 17. I've never done it with 4, but I know.
Yeah, I'm still using 4.
Yeah. Okay. What? I'm sure it's there. Apparently the AKO functionality has been around for a long, long time. So
and Peter,
pardon?
Everything I've done in like LT Spice version 4 has worked perfectly fine for me. So I haven't seen anything for me to go and change. However, if this is unique to this version, I may need to go and switch. Okay, the other thing too, I did a quick Google on what that TD is, and I found a hint where someone says check the help file. So if you go up to help and you look at the measure statement, they may define what TD means.
I'll do that, but the TD actually came from the person that I got this algorithm in the first place. How to measure rise time.
Yeah, they were saying because I just found a post on the LT Spice groups.io where someone was asking what value of TD they should use, and they said, why don't you go check the help file, because it explains the help file. Like if you go up right up there where it says help, you hit the help, and you go in there, it might be in there. Don't know. I'm just passing along what
Okay,
I read.
I'll take a look. Yeah, but Dave, I'm pretty sure you'll find that that step the step directive that I got in there as it's written and using the dot model 1 AKO and then your transistor value will work in your version. The reason why you got to go through this is because when you're using the step parameter list, it does not like to have all those letters in there like you get from the word model, and that's why you got to go to this kind of level with this AKO function.
Okay, Howard, go ahead.
Yeah, Peter, I think you mentioned it, but just want to confirm that when you go back to the legacy toolbar, that doesn't affect anything else in the new version?
No, it's just a which toolbar do you like?
Right. Okay. That's what I thought you said. Thanks.
And again, I don't know what else is in with the newer version as to that's different from 17. Because like I said, I only just downloaded it the other day, and then the computer blew up. So I finally got it all up and running, and I got a couple of programs loaded on here now. But I haven't had a whole lot of time to play with this latest version of Spice.
Okay. Thanks.
Okay.
Okay, anybody else? Questions? No, I guess not. Very good, Peter. That was cool. Someday.
That's my way of saying, you know what? Sometimes if you complicate things to make life easier, right?
Yeah, exactly. Okay, next up is myself. So recently, Dave made a version 2 of the DCR board, and I put it together. So I'm going to do a little presentation here. Entire screen. Oops. You see that?
Yep.
Okay. So this is the latest version of the DCR. Um, so at the top left here is the antenna in on a BNC. This is the VFO input. So in my case, I'm using the Park SIGGEN. We'll come back to that in relations to there's a pi attenuator here. This is 12 volts in. Coming around to the front on the right is audio out. And we have volume control. And this is a plug-in bandpass filter. So I'll come back to the filter and this attenuator. And there's an overhead shot. Can you guys see that? Is it too small?
Yeah, it's a bit small. If you have no trouble increasing it, then I'll do so. If not, we'll
I
suffer.
don't know if I can. I don't know if I can
Don't worry about it.
okay, cool. So we have the BNC connector here going into a bandpass filter. It's marked as QRP Labs filter, which I'm working on. But when the kit comes available, which is going to be very soon, I'm going to include uh, parts for a very simple bandpass filter so people can start working on this. And later on down the road, I'll do something with the QRP Labs filter. So it comes out of the filter, goes on to the input. It's mixed with the VFO here. There's the attenuator, and I've got a 50 ohm load hanging off that attenuator, because if we don't have this here, then the VFO becomes a current source for the chip rather than a voltage source. So that's why this 50 ohm load is here. Once the two are mixed, comes out as audio. We've got a volume control into a LM386 and out to an audio jack. There's the 12 volts coming in. We've got an LED for power. It feeds a 7806, and the 6 volts feeds the SA612, and the power jack has a diode in it for reverse voltage protection. Um, Now, in regards to this attenuator, um, the SA612 input spec, they're saying between 200 and 300 millivolts peak to peak, I guess. So the Park SigGen is much higher than that. So I had calculated a 15 dB attenuator for that to knock it down. And now the way the 612 works with the VFO is the higher your input signal is, the more gain you'll get out of the chip. But there'll be a point where you're going too high and you'll start distorting. There's been experiments done in EM RFD, and there's a couple of postings that people had tested that. Um, and also on the board, we have 2-pin headers for test points. So we have one here at the RF input. We've got another one at the RF output of the filter. Uh, we have another one on the bandpass spectrum coming out of the chip. We got another one for the VFO going into the chip, and we have one at the audio, and I think that is. Oh, we got another one going into the LM386. So the bandpass filters, the simple bandpass filter. This might be a little small to see. I had found this on the one of the forums quite a while ago, and this is the layout for the bandpass filter. This is one of the configurations that was recommended by the manufacturer. Uh, Disregard this resistor and this capacitor. This uh, passing capacitor is on the board already, and this resistor is not needed. But anyways, we have 2 capacitors and an inductor, and this person had designed this, came up with calculations for 40, 20, and 10, and I'm sure all the other bands could be calculated as well. So I will be including a bandpass filter for 40 and 20. And there's what's this one? This is the 40 meter bandpass. So we're looking at 7 megs. So it's pretty much centered on it. There is 20, and it's a little low. It looks like, and 10 meters. So all these graphs and schematic was supplied by that person on the forums. So this is what the bandpass filters look like, and very simple. You come in, there's the capacitor coming in to one side, and then coupled through another capacitor to inductor, and then the output goes to the SA612. Uh, Configuration is the same for both. Now, the reason I'm going with these for the kit is they're simple and they're inexpensive. If people want to experiment, they can build their own. The boards or the headers for it are spaced out for the QRP Labs filters. If you want to make up your own, go ahead. If you want to use a QRP Lab filter, go ahead. Just be warned that the QRP Labs output is 50 ohms. the input to the 612 is in the neighborhood of 1300 to 1500 ohms. And I think that is pretty much it. Now I did a recording, so I will share that. It's a couple minutes long, so let's have a look at that.
Ken, do you want to take any questions now before you get to the recording, or do you want to do the recording first?
Um, we can do the recordings. I can't see who's got their hand up.
Dave,
Go ahead, Dave.
you're muted.
Play the recording.
Okay. So I'm just going up the 40-meter band.
Do you have more volume there, Ken?
What's that?
Do you have more volume?
I've got everything up.
Okay.
Let's try that.
Yeah, it's not very loud, Ken. We're not picking up much. Certainly not as loud as it was this afternoon.
You know what? I'll post the video to the group. You guys can download and listen to it. Okay, that's it. Stop sharing. You guys weren't able to hear that at all?
Well, it was like this afternoon, Ken, where the CW at the very beginning was okay, but the sideband stuff near the up there wasn't coming through very loud at all.
Okay, because I checked and that button was turned on for the system audio. So
I know you got it to work better this afternoon, but it was kind of not very. Wasn't
that's
a
okay.
good.
I'll post the video on the groups, and you guys can, if you want, you can download it and listen to it.
Okay.
But it works pretty good. And the only thing left for now is the logistics of kitting this, finding out who wants one, and getting it out to people. And whether we're going to get together and build it or virtually or whatever. So we got to work this out. Okay, who was up first there? Go ahead, Michael.
the filter boards. Did you make like that's the same kind of perf board that I use and Charlie Morris uses and whatnot. Did you cut those yourself, or did you buy them with the four traces the right length, or what?
No, I cut it myself.
Okay, with a jigsaw, with a bandsaw or something. Oh,
With the utility
you can
knife.
you can score it. That's right. Yeah.
Yeah.
Okay. Thanks.
Or actually,
Okay. Good. Thank you.
I use a Dremel.
Okay. Fine. Thanks.
Go ahead, Dave.
Have to find the mute button. Yeah, Ken, there's those boards. If you send me the schematic, I'm not going to be able to do it before the eclipse. But after the eclipse, one of the things I could do, there's something called breakaway boards. I don't know how to do it, but there's a way of doing it in CPCB. It's basically you print out a bunch of those um, bandpass filters and you snap them and you break
Yeah.
them apart.
Yeah.
So we've got like 100 by 100. We could, you know, put a whole bunch of them on one square and order like 4 of those boards, you know, and we could have enough filters for everyone.
Okay.
And then
Well,
the nice thing is if you keep it generic, you could wind your own toroids and put different value capacitors.
yeah. Yeah. Uh, Maybe after the clip's done, do a check on what pricing's like for those things. Because they
Yeah,
got
well, first of all, I got to figure out how to go do it, but it doesn't matter. It's the price of the boards you're paying for. It
Oh,
doesn't
okay.
matter. You can do anything you want on the boards. It's just the way that you set up the boards in the Gerber files. You set them up to snap. I don't know how to do it, but the price will be the same for the boards.
Oh, really? Well, plus the cost of the bevel for breaking it off.
Yeah, that, as I said, I don't know anything about it. I'd have to go and look into it to see how it's done.
Yeah, we can take care of it afterwards. I got to start working on a bill of materials with DigiKey. It's amazing how much the prices of parts of DigiKey have risen before COVID. It's like some stuff has gone up for like 4 times the cost it was previously. And I think Peter's got his hand up.
I do, or I did. Ken, did you get a chance to run the filters through the SNA yet to make comparisons of what your bandpass filters are showing compared to what this other guy had done?
Um, no, because the SNA's at 50 ohm input. Those boards are 1300 or 1400 output.
Hmm.
That's why maybe a month ago I had posted something about doing a valid scan with the SNA where I took the output, put I think it was the 1400 ohm resistor in series with a 50 and hooked up the SNA across the 50 ohm one. And I had posted that I don't remember exactly if that 1400 ohm resistor in series would change the characteristics of it or not.
Now I can see where this is going to go to a rabbit hole, so we better be careful.
Yeah, I know.
Okay.
I know.
Right.
Look, I just want this to end. Anybody else? Cool. So there'll be announcements down the road when kits are available, what the price will be, uh, and we'll go from there. Like I said, we got to figure out how many kits we need, whether we're going to get together or we're going to do something virtually. Uh, that's all got to be decided by everybody what we want to do, and we'll let you guys know. Okay. Anybody else have anything? I think we're just a little bit after 9 right now. Okay. Shall we call it quits? Okay, gentlemen. Have a good evening and have a good week and a good weekend, and we'll catch you on it's the 3rd of April is the next meeting.
Thanks, Ken.
Thanks,
Right
Ed.
on.
Thank you.
Okay.
Right on.
Okay.